simultaneous spin-up and spin-down state of a particle. A two-state particle, in the context we will observe here, concerns a particle capable of having two distinct states of spin direction, spin-up and spin-down, denoted intuitively as shown. The spin operator, the observable representing the spin of the particle. For the first particle, in the compound space of the two-state particles is as shown, while the same operator for the second particle is as shown. In other words, to make an operator act on this four-dimensional space, we have to form a direct product of the identity matrix with the vector of the Pauli matrices. The vector of the Pauli matrices is the observable representing the spin of the particle in the two-dimensional space. Now, in the usual manner, we will make three simplifications. First, we will drop the coefficient h bar over 2 in the expressions of the operators. This will not affect the final result. Second, we will observe the vector of the Pauli matrices, directed only in z direction. Third, we will carry out the measurement not along just any vector, but along the z direction. Thus, we may now rewrite the spin operators in view of this new notation and show them explicitly in a matrix form. The basis states for the direct product of the single electrons, comprising a pair we are studying, are four, namely, we will observe one special state, in which our two spin s particles can supposedly exist, namely the so-called singlet state, which at the conditions of our discussion is written as shown. Now, if we are to carry out an experiment to determine the spin of the first particle, we have to act on this ket psi with the operator s sub 1. We can determine, using the rules of quantum mechanics, what will be the probability that after the measurement, that is, after the application of one or the other, s sub 1 or s sub 2 operator on the single state function psi, the first particle will have spin plus, that is, will be in a spin-up state, while the second particle will have spin minus. Alternatively, what is the probability of the first particle to be spin down while second particle to be spin up, when s sub 1 or s sub 2 are applied? Indeed, according to the rules of quantum mechanics, the probability to obtain eigenvalue 1 of operator s sub 1, that is, the probability to obtain one of the two eigenvalues of the operators, is calculated in this case as shown, where bra I stands for the vectors of the orthonormal basis. Obviously, when dotting the vectors of the basis, that basis being orthonormal, into the above singlet state vector psi, the plus plus and the minus minus terms in the sum will be 0, while the plus minus, respectively the minus plus basis vectors, will give unity with the corresponding component vectors of the single state psi. So, we'll get Let's write again the equation which this result came from. We can see now that the probability that as a result of the measurement with the operator s sub 1 the probability to obtain state of the first electron plus, while the state of the second electron minus is 50%. On the other hand, the probability that as a result of the measurement with the same operator s sub 1 the probability to obtain state of the first electron minus, while the state of the second electron plus, is also 50%. Similar will be the case with the operator s sub 2 and its eigenvalues and eigenvectors. So far this is a well-known state of affairs. In other words, both operator S sub 1 and S sub 2 may produce vector plus minus, describing the state of the two electrons after the measurement, that is, after they are applied on the singlet state vector psi. And for any of the two operators the probability to obtain ket plus minus is 50%. And, alternatively, we want now to know something more, which hasn't been noted so far. We want to know what will be the outcome of the measurement if the two operators S sub 1 and S sub 2 are applied simultaneously on the singlet state function psi. For this reason we need to explore whether or not the two operators, namely S sub 1 and S sub 2, can have simultaneously the same set of eigenvectors. As is known, a criterion for two operators to have simultaneous eigenfunctions is their commutator to be equal to 0. In other words, we have to explore whether the following equality is true. This can be checked immediately. As can be seen above, the two products are identical, which implies that indeed the commutator is 0. This, however, means that the operators S sub 1 and S sub 2 have simultaneous eigenvectors. However, if that is the case, then the simultaneous application of S sub 1 and S sub 2 on the state psi may lead to a situation whereby application of S sub 1 will bring about the eigenvector ket plus minus, while the application of S sub 2 will bring about the eigenvector ket minus plus. This is an algebraically viable situation since the operators S sub 1 and S sub 2 share simultaneously these two eigenvectors, as was seen. This outcome of the measurement brings about a confusion from a physical point of view as to what exactly the subsequent state of the electrons is. For instance, it is seen from the obtained result that the subsequent state of the first electron after the measurement done with S sub 1 will be spin up, while the subsequent state of this same first electron, but as a result of measurement with S sub 2, has to be spin down. Therefore, according to this argument, in 50% of the cases after the measurement the first, and respectively, the second electron, will be at once both in spin-up and spin-down state. This outcome of our thought experiment, however, is contrary to the laboratory experimental observations. So far an electron existing simultaneously in spin-up and spin-down state has not been observed experimentally. One may even argue further that in allowing for the very possibility for both first and second particle to be spin-up in a collapse state, that is, for the possibility the subsequent state to be ket plus plus, respectively, ket minus minus, we in fact allow for the possibility for a state the probability of whose establishment is 0%. In other words, the two observers cannot make it so that through their measurements the final state to be ket plus plus, respectively, ket minus minus. This is an argument which rejects the mere possibility for simultaneous measurement carried out by two observers, because at such measurement a situation may be encountered whereby an improbable final state will be established such as ket plus plus, respectively, ket minus minus. However, there is nothing to forbid, as far as a physical experiment is concerned, to experimenters from carrying out simultaneous measurements on this system. In other words, if an observer carries out an independent but simultaneous measurement on the second particle, according to the above example, that observer may find out that the probability of getting spin up or spin down may not turn out to be 50%. This will be due to the fact that unsuspectedly someone else is carrying out simultaneous measurement on the first particle. As mentioned, there is nothing to forbid two independent observers from carrying out measurements on each one particle simultaneously. but not getting 50% probability goes contrary to the result, established on the basis of quantum mechanical principles, that the probability must be 50%. This one single example of discrepancy of the methods applied by quantum mechanics and reality is enough to indicate that those methods are flawed, and that quantum mechanics has no place in science. The above analysis shows that even if one considers quantum mechanics as only a formal tool for solving practical problems, by just following and applying its recipes, as is usually done throughout universities, the using of its machinery itself poses problems, by getting one into unacceptable non-physical situations.